probably more a lecture, I think, than a talk, is the moons of Jupiter, of which there are 95 confirmed to date, and there's at least 10 more that have been detected but are yet to be confirmed. Now, you may or you may not have heard about the 4 large moons of Jupiter, the Galilean moons, but most people have probably never heard of the other 91 smaller moons. So I usually spend about 5 minutes talking about each of these. So I hope you're not busy tomorrow or the next day. We'll be here for a while. Yeah, bring out the coffees. So tonight we're going to have a look at these smaller moons as well as the better known Galilean moons. To start with, does anyone know what this might be? It's not a whole lot of objects. Any thoughts? Io, someone said yes. It's infrared picture of Io. And what about this bright dot? This is actually travelling around the North Pole of Jupiter. So that's actually ultraviolet. This is visual. So does anyone know what that dot might be? Probably if you were at this talk a few years ago, which I did. It's an aurora. But what about that particular white, or that particular bright dot over there? It looks like it's moving around. It's related to the other picture. Oh, well, we'll find out later. It is. It's a thing called a flux tube from Io, which we'll have a look at later on. So it's quite fascinating. Now, I'm going to start by explaining what a moon is and where Jupiter is. And then we'll have a quick look at the 8 regular moons, including the 4 large ones. Next, we're going to head way out from Jupiter and look at these often neglected irregular moons. And finally, we'll come back in near Jupiter again and have a look more closely at those 4 large Galilean moons, which have a lot of incredible features. And each one could almost have its own talk. There's so much to talk about those Galilean moons. So 2 important questions to begin with. First of all, what's a moon and where is Jupiter? And since this talk is about moons, you're probably wondering exactly what is a moon. So here's one I prepared earlier.
That's a new one.
That's no moon. It's a space station.
Okay, Obi-Wan Kenobi, it was a bit loud, mate. So obviously I'm wrong. That's a space station and not a moon. So there's really no formal or scientific definition of a moon. It's pretty much anything natural that orbits a planet or a dwarf planet or even an asteroid is a moon. And this, or otherwise known as a natural satellite, this is an example of an asteroid with a moon. This is asteroid Ida here, and its little moon Dactyl over there. These live in the main asteroid belt between Mars and Jupiter. So it's quite small. That's only 56 kilometres with a tiny little 1.5 kilometre moon, Dactyl. So moons around asteroids are not too uncommon. And compare that with our nice spherical moon here. And then over Mars, we have Mars over here with its 2 very small, oddly shaped tiny moons, Phobos, about 27 kilometres wide, and Deimos, about 16 kilometres wide. And so that brings us to the question of where is Jupiter? Well, here's Earth over here, 150 million kilometres away from the Sun, or 1 astronomical unit. So an astronomical unit is about the average distance between the Earth and the Sun. The exact definition is 149,500,000 and all those numbers. And that's exactly to the nearest 700 metres. And it's defined like that to make calculations easier. Long story there, but it's like the second has been redefined and the meter's been defined. Everything's been defined to be a lot easier for the calculations. So using astronomical units makes life a lot easier. We can talk about distances, so like Earth to the Sun, instead of all that, we can say it's 1. And then way out here is Jupiter, which I better get out of the way of. Jupiter, a little over 5 times as far away from the Sun as the Earth, 5.2 astronomical units. It's just under 780 million kilometres on average, and here's Mars quite close to us over here. Now, there are actually 8 moons orbiting around Jupiter, around its equator, in the same direction that Jupiter rotates, and in fairly circular orbits, or nearly circular orbits. So we'll have a look at these ones to start with. Now, through a small telescope or even a good pair of binoculars, you can often see the large Galilean moons as 4 little bright dots next to Jupiter. These were discovered by Galileo in 1610, but it was actually another astronomer Simon Marius, he looks like a bit of a evil genius kind of in that picture. He was actually on the front of his book from 1614 apparently, so he must have been happy with the picture. But so he discovered them apparently around the same time, and he's the one who named them Io, Europa, Ganymede, and Callisto. And those names come from characters in Greek mythology. Now, if we have a look at these orbits from above, we can see Callisto, Ganymede, Europa, and Io. But Io is not the closest moon to Jupiter. There are 4 more moons within those 4. So these 4 are very small, quite close in. The names, which I had to look up how to pronounce, are Metis, Adrastea, Amalthea, and Thebe. And so you can see, for example, Adrastea is only about 16 kilometres wide. Compare that to Ganymede, about 5,300 kilometres wide. So those little ones, little pictures there are more to scale. They just zoomed in because that wouldn't be much good, just kind of explain what's happening there. And so Adrastea is about the same size as Mars's Deimos, very small. Amalthea is about 250 kilometres wide, so that's actually the 5th largest moon, that little tiny dot up there. So if we have a look at this inner group of inner 4 here, they're called the Amalthea group. Gets a bit hard to say all these names after a while, especially when you go through all 91 of them. Now, it's named Amalthea after the largest one in the group. It's possible that these are parts of a larger object that broke up in the past, but it's more likely that they formed separately and just never conglomerated into one object. It's a bit like the asteroid belt, which is not a broken up planet. It's a whole lot of asteroids which just never formed one planet, probably mainly because of the gravity of Jupiter preventing them from joining. Now, there's a fun fact about Amalthea. I should first of all point out, that's a picture from Voyager 1 back in 1979. And that's an artist's impression to give you more of an idea of what it might look like. This is one of the rarest objects in the solar system, and it's likely to be due to material from Io's volcanoes. So you can see Io up there and Amalthea there. So Io spreads its sulfur compounds all through the system. In fact, Io loses about 1,000 kilograms per second through its volcanoes, and between about 200 grams and about 1 kilogram lands on Europa per second. So Io is really spreading a lot of stuff around the system there. Amalthea also seems to radiate more heat than it receives from the sun. Now, the thoughts there are that it may have an electric current set up within it as it orbits through Jupiter's magnetic field, and that could be causing a current, giving it a bit of extra heat, as well as possibly due to tidal forces. So as it orbits Jupiter, it gets a little bit closer, only minutely closer and further away, and that's enough to stretch and squeeze it, which could warm it up, and that happens with quite a few of these moons. So that might be the reason that is warmer or sending out more heat than it receives from the sun. Now, something really interesting, Metis here only takes just over 7 hours to orbit Jupiter once, and it's travelling at 32 kilometres per second. That means Hamilton to Auckland in 3 seconds. It's going pretty quickly. Or even from Earth to our moon in less than 3.5 hours, and that's about 40 times the speed of the average bullet, apparently. So that's going around pretty quick around Jupiter. In fact, it's going around Jupiter faster than Jupiter rotates. Adrastea is very close to Metis in its orbit, and it's only about 5 minutes slower as it goes round. So they're very close together. So 2 very fast speeding moons shooting around the inner area of Jupiter there. Now, you've seen a wide range in sizes already, and the sizes of Jupiter's moons range from Ganymede at near 5,300 kilometres, which is about 1.5 times the size of our moon. Then we have quite a big jump down to 170 kilometres. Now, that's Adrastea. That's its average size. So if you take all the different dimensions and work out the average, it's about 170 kilometres. Then all the way down to number 91 at about 1 kilometre in size. But there are probably another 500 to 600 moons estimated out there, less than a kilometre in size, orbiting Jupiter. And because there's no definition of what a moon is, then they can get really small. And I think it just probably comes down to common sense when you get to something pretty small and say that little pebble is not a moon. So I don't know where you draw the line, but there must be some limit that someone will have to put on at some time, I'd imagine. And I haven't really shown you a size comparison of Jupiter with the Galilean moons. So here are the Galilean moons over here: Io, Europa, Ganymede, Callisto, and Earth and our moon to scale as well. Obviously not the sizes, but not the distances, but the sizes. And here are the distances down here. Earth to the moon is just a little bit smaller than Jupiter to Io. So if you see that first dot down the bottom, that would be about where Earth to our moon is, just a little bit more. So now, just for fun, here's Jupiter with Amalthea. Now, I don't know if anyone can see it. Amalthea is a tiny little dot. And if you look at the red spot, you can see a little dot there, but not on the other one. Now, this was only taken a year ago, March 2024. And so that was by the Juno mission, so that's quite a recent picture. And just to be fair, I'll just give you a zooming in here. So there's Amalthea, that little tiny blurry dot, and there's a shadow on Jupiter. So that'd actually be an eclipse. So if you're sitting in the clouds here, you'd see Amalthea moving in front of the sun. It would be a partial eclipse, because I think that would be smaller than the sun at that point. I haven't really worked that out. So you might wonder why those little tiny inner moons are called regular moons, along with the giants, especially when they're such a weird shape. Well, it actually has nothing to do with their shape at all. So before we go there, we'll just have a quick recap here. I said we have Jupiter has 95 confirmed moons. The 8 we've seen so far are classified as regular moons, and the other 87 as irregular. And so regular and irregular refers to the shape of the orbit around Jupiter, or around any planet if we've got a moon going around any planet. So we'll explain that one fully soon. The 8 regular moons are generally formed with their host planet as opposed to being captured objects. And the 87 irregular moons are captured objects, asteroids, comets, or other small objects which have been captured by Jupiter's gravity. And what we see now, interestingly enough, the 87 irregular moons were probably only 7 or 8 slightly larger objects in the past that broke up. And I'll show you how we can work out what those actually were, or where each moon came from, and actually group them together. And so we can group them by the orbits, their orbital characteristics, and by the colours, which pretty much indicates the materials. So if we had a whole lot that were a certain grey colour and some of that were a bit more of a red colour, you can probably say that it might have come from the same original object. So that indicates their origin, where they came from. Now, it does help to know some simple ideas about orbits before we go on here. All objects don't orbit other objects in perfect circles, although some orbits are very close to perfect circles. And an orbit's really a squashed circle called an ellipse. And the same applies to all orbits, whether it's planets around stars or moons around planets, or even binary stars where you have 2 stars orbiting each other. They'll be in an elliptical shape. And but for tonight, I'm just going to keep it simple and say moon orbiting a planet, so I won't try and describe every time each different thing orbiting something else. Now, this is a more extreme example of an elliptical shape. The more squashed the orbit is, as you can see in this case, the further away the planet is from the centre of the orbit. And if you remember from your high school maths, the 2 points here and the same one on the other side are called the foci of the ellipse. So the planet will sit in one of the foci, or the focus of the ellipse. And as the moon orbits this planet, it speeds up as it goes towards the planet, which makes sense, it's kind of falling towards it. Maximum speed near the planet, slowing down, and minimum speed at its greatest distance. Now, it doesn't stop really, it's just that PowerPoint wants to stop and then carry on. So that would be quite disastrous if it really stopped. So that's the general idea. Of course, if you had a circular orbit, the planet would be in the middle, so the foci would move towards the centre of the orbit. Its eccentricity is the word we use to describe how elliptical the orbit is. And a circle is an ellipse with no eccentricity. The Earth's orbit around the Sun is almost circular. In fact, it'd be very hard to tell that it's not just by looking at it. Even with this graphics here, I think the difference was less than a pixel, so I had to draw a circle. So the Earth's orbit is 0.0167, but that's still enough with our orbit to be a few thousand kilometres closer and further away at different times of the year. The middle column is just a few examples of more elliptical shapes. And over on the right-hand side, we have the orbit of a planet, an exoplanet called HD 20782b. And it's given that name because it orbits a star because the star is HD 20782. And one day it might get a real name. Now, its eccentricity is 0.97, which is about the same as Halley's Comet around our Sun, so it's quite elliptical. Some comets even get up to near 1. This comet here is 0.9999 is the, actually I think it's 0.999915 is the eccentricity of that comet. So that's out from out in the Oort cloud. It virtually is falling towards the Sun, around the Sun and back out over tens or hundreds of thousands of years. So there's a big range of these eccentricities. Jupiter's moons mostly I think are about 0.5 or less, but that's enough for us to be able to classify them quite nicely. Now the next thing is the angle of the orbit with respect to the equator. And this is called the inclination. Now, Io and the other 7 regular moons orbit pretty much in Jupiter's equatorial plane, and so the inclination angle for them is just about 0. So there's little Io, that little dot there, and a bit of a zoom in up over there. And that's to scale pretty much the distance, Io to Jupiter. Now, another one of Jupiter's moons, Carpo, has an inclination of 51.4 degrees. So that's getting up there. That's a very high angle. And its orbit is so big that it can't fit on this picture. We have to zoom way out. And there's Carpo, actually gets to over 24 million kilometres away from Jupiter. So it's pretty big, but it's not the biggest. There's another one. This is S2017J6, which gets to 35 million kilometres away from Jupiter. This one takes 683 Earth days to orbit once, nearly 2 years. And there's another one called Cora, which takes over 2 years to orbit Jupiter once. And just in case you're wondering what these weird names are, these are provisional names. When a moon is first discovered, or when any object is discovered in the solar system or anywhere, it's given a provisional name. So if I look at Carpo, for example, before it was given the name Carpo, it was the 20th Jupiter moon discovered in 2003. So S for satellite, then the year, then the first letter of the planet, and then the order of discovery. This poor guy up here, J6, sixth moon discovered in 2017, has been waiting 8 years for a real name. I don't know why, it hasn't got a real one yet. But it may get one day. I think when I first did this talk, it had only been waiting about 4 years, but now it's 8 or so. So it's, yeah, taken a while. So the permanent name, Carpo, is the one that one's waiting for. And you may kind of look at that and think, oh, how does Earth and its moon look compared to that? Well, if we jump down here, this is the orbit of Earth, Earth's moon around Earth. So a little blue line in the middle is where Earth would be. Our moon, 384,000 kilometres and 384,000 kilometres out the other side. Not too different to Io. And so you can see just how big that Jupiter system is compared to our little tiny Earth-Moon system. And that took us 3.5 days to get there with Apollo. So if we'd been, if we'd had something that far away, well, it probably wouldn't stay near Earth, but if we had something that far away, I don't know if we'd ever would have got to it by now. We'd still be waiting. So that's all to scale, which is quite amazing, really, just to see how big that system is. Now, this might look a little bit meaningless to start with, but I think it looks nice and it's quite pretty and it's got nice colours. So apart from that, it's now a plot more than anything. Jupiter's not in the middle of this one because it's a plot. I've just got each of those lines, the centre of each line crosses in the middle. And it's a comparison of the orbit size and inclination between just a few of those irregular moons. Now, I've coloured it to highlight something really interesting, which you may notice, but I'll point it out, that some moons seem to have very similar orbital characteristics. So the size of the orbits and the inclinations of some of those moons kind of seem to fit together quite nicely. So if we look at this group here called the Himalaya group, the Himalaya group has 9 moons in it. I've just drawn 4 there, but you can see they're all about the same length, so the same size orbits and about the same angle. It's called the Himalaya group because that's the largest moon in the group, even though Himalaya is quite small. And then this one here, the Kame group, is kind of a similar thing. If we look over here, this group here, that group there, and that group there. And so it's almost as if each group was a single object that was smashed up in the past, which is obviously what I'm getting to, but we'll have a bit more of a look at that idea shortly. So the final little bit of information about orbits is that a moon might orbit in the same direction as the planet rotates, if I can work that out myself, and that's called a prograde orbit. So if we are looking down on Jupiter from the north, Jupiter is rotating anti-clockwise, so any moon that orbits anti-clockwise looking down from the north is in what we call a prograde orbit. If it orbits the other way, opposite to the planet's rotation, it's called a retrograde orbit. So that makes sense so far. And just a quick summary of those so far. I haven't mentioned actually the semi-major axis. I think we did have a look at that at one stage, but that's really just the size of the orbit, the distance between the centre and the most distant part of the orbit. For a circle, that's the same as the radius. So it's really just the size of the orbit, really, is what we're talking about. Now, an orbit can be, as I mentioned, a circle or a squash circle, an ellipse. We can look at the angle, the inclination, the angle to the equator, and we can look at the direction. It can either be going the same way the planet rotates or the opposite direction, so prograde or retrograde. Now, with that information, we can classify a moon as regular or irregular. So it's getting a bit easier now to do this. We can say that if a moon has a prograde orbit and the orbit's nearly circular and the minimal inclination, it has minimal inclination, then it is a regular moon. Now, when I say minimal inclination, it's kind of below 26 degrees because there are no moons in the solar system with an inclination between 8.3 and 26. There are moons from 26 to 57 and 0 to 8.3. So you could probably say that if a regular moon has an inclination of less than about 9 degrees, you could probably cover that, but for some reason they just go all the way up to 26. But the reason there's nothing between 8.3 and 26, I don't know if that's something to do with just dynamics or if we just haven't found anything in that range at this stage. Now, a regular moon is most likely to have been formed with a planet. And you can see how that would work. If we start with a disk of gas and dust that's rotating, and then a planet coalesces in the middle, it's obviously going to be rotating that same way. And if a moon coalesces in that gas and dust, it's going to be going around the same way. So you can see that it'd be pretty hard to form a moon going the other way with the planet. So regular moons are most likely, or almost certain, to have formed with the planet. And all the other moons are irregular. And that means if the orbit is retrograde, it's classed as irregular, even if it's a nice circular orbit, as are moons with a very high inclination or high eccentricity, and that doesn't matter which way they orbit. If they're very eccentric and very highly inclined, they will be irregular. And you can probably guess irregular moons are probably generally captured objects, as they will come in from different directions at different angles, and be very unlikely to come in, get captured, and end up in a nice circular orbit. So we've got those two different ways of moons being captured or formed. So quick reminder, here are all 95 of Jupiter's confirmed moons. We have Io, Europa, Ganymede, Callisto, and here's the others. The others are quite small and hard to see, so I'll zoom in for you there. So here are those other 91 moons. These are just dots because if I drew them any smaller, you wouldn't see anything. You can barely see them as they are. So the first two are Amalthea and Himalaya. we'll say 170 kilometres on average, so 250 plus that, plus the other direction averaged out. Himalaya just less than 170. These two are artist impressions. Tibet about 100 kilometres. Alara, Metis 40. Then all the way down to the Misto, getting quite small down at about 8 kilometres wide. And all the way down to Little Valetudo at 1 kilometre. So all these ones in between are between 1 and 2 kilometres wide. So we say, you know, Jupiter's got 91 moons, but they're very small, little tiny things. These then are the 8 regular moons. They're all prograde, almost circular orbits, and orbit close to the equatorial plane. I'm going to zoom out, but I will come back to these 4 at the end or later on. But now I just want to go further out from Jupiter, and we'll try and make sense of those irregular moons. Now these are the orbits of most of the irregular moons. And at first sight it looks like a bit of a mess. The reason for that is that it is. But now you know something about orbits, I can show you how to make sense of this all. So we'll now be able to kind of break this down and kind of make sense of that horrible mess there. So here we are looking top down now, looking from the north down towards Jupiter. Those red lines show retrograde orbits, all the other ones are prograde orbits. And when you look at Carpo and Valetudo's orbits, there you can see why there's probably collisions with different directions, like going down a highway with everybody going in different directions. So collisions and bits and pieces broken up. Valetudo is the only one discovered in its group so far, but it's almost certain to have a whole lot of small pieces around it because it's almost certain to have collided with other bits and pieces. Now, to make sense of this, we can take any of these moons, and we'll just take one. We'll start with this nicely named one, 2018 J4. Now, we know that this one has a semi-major axis, that distance of about 16.5 million kilometres. And we know that its inclination angle is 53.2 degrees. So we'll plot that point on our graph. Then we'll take another one, Valetudo, that's about 19 million kilometres for that size, and it's about a 34 degree angle. So plot that one, then we'll go ahead and do them all. And you can see that there does seem to be something happening there. There do seem to be kind of groups appearing. And so from that mess, we're starting to be able to analyse and just see that the connection is occurring between these objects. So these are coloured now to sort of give a bit more of an idea. I'll just go one more. It's getting similar to that plot I showed you earlier, but this time with all of the irregular moons. Now you might look at the purple group, the Pasiphae group there, and you'll see a couple of the purple dots kind of look like they're close to the red ones there, and you might think, well, how can you possibly put that in a group? Well, there is the other bits of information, a semi-major axis against the eccentricity, then looking at the colours, like I mentioned before, and a few other bits and pieces. So it does work out that they seem to be the most likely groups. The Himalaya group and the Carpo group and the Kame group are all pretty clear, and Misto on its own and Valetudo on its own are obviously groups on their own. So what is now 87 irregular moons was probably only 7 or 8 originally, and that's how we can kind of group them together by looking at this, looking at these orbital characteristics. Now, to be clear, I should say this does not mean that all the moons in a group orbit together. So that's not how the moons in the Himalaya group, for example, orbit. Instead, the orbits precess around Jupiter. So in the end, they're actually all over the place. So although they're all over the place, those orbital characteristics still remain, even though the orbits have shifted around. They're still the same shape and same angles. So if you imagine 9 moons in that group and then the other 87 minus 9, so 87 altogether. And it's just quite amazing that we can break it down into these groups by looking at that information, actually analysing this information. And looking at it from the side view kind of shows that it's, well, same kind of mess really, looking at it from the side, but they're all kind of the same close angle. Obviously very sped up because these moons range from between 252 and 287 Earth days to go round Jupiter once. So 95 moons today, probably because some are broken up during capture or since being captured, or a bit of both. Probably just this number of moons now. So altogether, maybe 8 irregular moons and 8 regular moons, so maybe about 16 objects originally. So that kind of tidies it up a little bit for those of you who don't like to see the mess that's out there. The other thing is, yeah, these original moons are still not much bigger, or these original objects are still not much bigger than what we see now, and they're still way smaller than the Galilean moons. So now we're going to have a closer look at the Galilean moons, the 4 big ones. So these were discovered in 1610 by Galileo, and that's why they're called the Galilean moons. And the picture's quite nice without the words too. It's just a collage, that one, so they don't sit like that, but they look quite nice. That's an artist's impression of Aurora on Ganymede over there, and that's actually the infrared picture from earlier overlaid on Io, and then Jupiter in the background there. So Galileo named them Jupiter 1, Jupiter 2, Jupiter 3 and Jupiter 4, and I mentioned before that Simon Marius, who apparently discovered them around the same time, is the one who named them Io, Europa, Ganymede and Callisto. And these modern names have only really been used since about the mid-1800s, so about 1850, I think that's when Amalthea was discovered, and then more and more were discovered. Now these distances from Jupiter, approximate, just rounded to the nearest 1,000 or so, with Io about 422,000 kilometres away from Jupiter, a little bit further than our moon from Earth, which is 384,000 kilometres. Now 3 of these moons have managed to get themselves into what we call a 4-2-1 orbital resonance, and that means for every 4 orbits of Io, Europa makes 2 orbits and Ganymede makes 1. And that means that they can line up like this, and with Io having an orbit of about 42.5 hours and Europa having an orbit of twice that, 85 hours, and Ganymede at 170 hours, lining up like this, 42.5 hours later, they'll line up like this, and so on. And if we just have this little line appear showing when they line up, so you'll see that Io turns up in every single lining up. So 42.5 hours plus a few in between with Io and Ganymede. Callisto doesn't get included. That's not in the resonance. So in the future it might get closer and end up being in an 8-4-2-1 resonance, but at the moment it just sits out there, just doing its own thing. Now, this repeated lining up means that they can't quite settle into circular orbits. They're giving a little tug on each other as they go past each other, and so that just slightly pulls them out of being in a circular orbit. And as you saw before with the elliptical orbit, they'll be slightly further away from Jupiter at times and slightly closer. And that leads to something called tidal heating, which means that the gravitational pull of Jupiter changes on that moon during its orbit, which stretches it and squeezes it a bit. And although the difference in the orbit size is not that great, it's enough to keep these warm and for interesting things to happen with them. So let's first of all have a look at this. This is one of the fun things that happens when you're in these resonances. This is a double eclipse with Ganymede and Europa. So you can see the 2 shadows, and the shadows overlap. So if you were in the clouds there, you'd see the sun, you'd see one of the moons coming along, then the other moon coming along, and you'd see a moon in front of a moon in front of the sun. And so that's quite a neat thing to have happen. And there's another interesting event here from 2015, fairly common as well. This is a triple transit. So although the shadows don't overlap here, there are 3 shadows on Jupiter at the same time. A little bit more exciting than what we get here, but here's a little bit of an animation that shows what's happening. But you can probably guess from the other image I showed you what is happening. This one involves Callisto, which is not in that resonance, but of course it can get in between the other, in line with the other 2 at certain times. So a little bit less common, but some pretty amazing things. Then we saw before Amalthea putting a shadow on there as well. So I guess there could be times where you could have a you could have 3 shadows in a row because Amalthea is going around so quickly. You might actually end up with three moons in the sun behind you.
Just point out that these can be seen visually in an amateur telescope.
Yeah. So the transit, yes, actually that's a good point, because this one here was actually taken from Earth. So this is a whole lot of photos that were put together. Oops, go back again there. A whole lot of photos that were put together. So even though it's a bit grainy, it is pretty remarkable that this was actually taken from Earth. This was by Christopher Go in the Philippines. So yeah, so you are pretty lucky. Yeah, okay, so that's pretty cool, yeah, which you can sell us. An Astron's telescope. This one is made up from Hubble images, but of course you could actually see that as the same kind of thing. In fact, I think when this particular one happened, I think it was cloudy everywhere, which is often the case with astronomy, looking at things. So I want to show you these moons in a bit more detail now. And as I mentioned, there's so much you could say about each of these Galilean moons that they could all have their own talks. But we'll just stick to some of the more interesting facts tonight about these 4 moons. This is Callisto, and this was taken by the Galileo spacecraft in 2001. This is the 3rd largest moon in the solar system, and it's the most densely cratered object, and you can probably see why it might be the most densely cratered object. Here's Jupiter, the largest planet, which is going to attract a lot of asteroids and comets. And there's Callisto, the largest of the 4 moons, of the 4 large moons. Oh, sorry, the most distance of the 4 large moons. So it's going to get quite a lot of this stuff hitting it before it gets into the inner system there. So it's kind of going to protect the others. Its surface is also the oldest surface in the solar system, about 4 billion years old. So it doesn't get replaced or replenished by ice or anything coming up from underneath. And so the craters just stay there. It is an icy moon, even though it looks dark. There's just a lot of dirt and debris on the surface, and you can see that gets cleared away as the meteorites hit it and just kind of throw the dirt and dust away and uncovers that bright ice underneath. Now, here's something you might not have seen before. This is a photo taken by Galileo spacecraft in 2001. These are ice spires, which get to about 80 to 100 metres high, just taken up from, they're about those 2 areas on Callisto up there. And a nice artist's impression gives you an idea of what it might be like to be on the surface looking at those. It's thought that these are possibly, or most likely, material thrown up from a giant impact billions of years ago. Would have thrown the icy, dirty shards away from the impact. The dark material seems to have slipped down to the lower regions, leaving the icy points, and they will be eroding very slowly due to micrometeorites and other impacts. Even some of the radiation particles are probably slowly eroding them, taking a long time. But give you an idea of the size compared to a person. That'd be about the height of a person there, and there might be another person up the top. So I'll pick on Andrew. There's Andrew at the top. There's me at the bottom there saying, yeah, nah, I'm not going up there. The radiation will be pretty deadly, but you can enjoy the view for a little bit anyway. So there you go.
Sorry if I may.
You may.
The entire surface looks like.
No, they've only got these photos just from a couple of areas there. There may be more in other places, but these photos here were just taken around those 2 areas there. Now, the Galileo orbiter detected an induced magnetic field around Callisto. That would indicate, or could indicate, that a saltwater ocean might be present. So how does that work? Well, Jupiter's magnetic field would set up an electrical current in the ocean of Callisto, and these electrical currents in turn would set up a magnetic field. So that's something you may remember if you carried on with your science at high school, about electric fields and magnetic fields being able to induce each other. Now, there's very little tidal heating of Callisto, so that means an ocean or a liquid ocean would need a lot of ammonia in it to prevent it from freezing. Either that or material below the seafloor would have to have a bit of radioactive decay going on to heat it up. So if the ocean is there, it's probably only a few kilometres deep if there's no ammonia present, but if there's ammonia present, it could be up to 100 kilometres deep. You might notice that there's no core in Callisto too. The reason for that is that it's pretty certain astronomers think that it cooled down too quickly for a core to form, so too quickly for the heavier material to sink to the middle, and so it's just a mix of ice and rock. Of course,
it's spherical, and yeah.
It's still, yeah, so spherical, but just cooled down too fast for all the internal parts to sink. Although it's possible that when the JUICE mission gets there and studies it, we might find something different, but models and ideas seem to fit this idea at the moment. Now, the ice crust would probably be about 250 kilometres thick based on the models for this moon. But having said all that, the induced magnetic field could actually be due to interactions between Jupiter's magnetic field and Callisto's highly ionised upper atmosphere. So that could also give the readings that an ocean might give as well. I think, again, the JUICE mission, which gets there in the early 2030s, will probably give us some more information about that as well. So it's going to be interesting to find out if it has got an ocean. So we'll move on to Ganymede now. This is Ganymede, which is the largest moon in the solar system. Now this one has a natural magnetic field. It's the only moon in the solar system to have a natural magnetic field due to an iron core. It's like a planet would have. So it looks a lot like our moon with its colours, with the greys and the browns, but again, it's an ice moon, and it's just dust and debris that's colouring it, the darker colours. And again, the meteorite impacts have cleared a bit of the dirt and dust away, so you can see the bright spots where meteorites have hit the surface. Now, under the ice crust, this almost certainly has an ocean, 100 kilometres deep, and that gives it as much, well, it gives it 6 times as much water as all of Earth's oceans put together. And that would make it the biggest ocean in the solar system. It's possible Titan might have a deeper, deeper ocean. Titan is the second biggest moon in the solar system. It's one of Jupiter's moons and may have a deep ocean as well. But this is almost certainly at this stage seems to be the deepest or the most voluminous ocean. Now it's probably saltier than the Dead Sea as well. Again, this is from induced magnetic field readings from spacecraft that have orbited around. This ocean's between 2 layers of ice. We have regular ice on top, which is just like our ice, ordinary water, which is less dense than water, so floats to the top, and a higher density ice, still water, still H2O, but a different configuration of water molecules. It makes it higher density, and so it stays at the bottom of the ocean. And so that seems to be the most likely form for the ocean on Ganymede. There is another model, however, that indicates the possibility of maybe 4 ocean layers. And in this case, each ocean would be saltier than the one above it, and each ice layer would be a higher density than the one above that. This has been worked out with various models which seem to fit the data, but it's also thought it could be an unstable configuration. So if it does occur, it may be something that just happens at times, so it may freeze out and then it may melt again and turn into an ocean, well, a single ocean, then kind of freeze in layers again, so it may be a periodic thing, or it may not happen at all, but it seems to be a model that was put forward about 10 years ago that seems to have some, seems to have a bit behind it, so it may be the case. Again, we might have to wait for the JUICE mission to get there in 2030s to give us more information about that. Now, all of the Galilean moons have auroras, and these are caused by charged particles around Jupiter interacting with their very tenuous atmospheres. And the atmospheres are, probably you'd call them exospheres, where the particles are so far apart that, not like our atmosphere where the molecules hit each other, but the particles are so far apart they never even touch, so it's very, very thin atmospheres, but enough to give auroras. But due to its natural magnetic field, Ganymede has auroras kind of in a circular oval shape just like the Earth does. And this is an image of how the magnetic fields might look around Ganymede. And so just like on Earth, where the particles coming, well in this case from Jupiter, not the Sun, would be directed towards the north and south poles. So there would be northern and southern lights on Ganymede. That's an artist's impression. But it's thought they would be a very deep red colour. In fact, if you're on the surface, maybe you might see something like that. The aurora are meant to be 15 times as bright as the aurora on Earth, but because they're a deep red towards the end of the visible spectrum, it kind of cancelled out for our eyes. So if you're looking at them, you probably still have a bit of trouble seeing them. So it'd be quite a sight there, I guess, if you were able to stand there for 48 hours of life. It's not fun out there. And I think I mentioned before, Ganymede also has a secondary magnetic field, and this is an induced magnetic field from its ocean. So it actually has two separate magnetic fields. And the same as with Callisto, induced by the magnetic field of Jupiter, creating currents in the ocean, forming a second magnetic or induced magnetic field. So now we get to maybe a better known one. This is Europa, which has twice as much liquid water as the Earth, and it's in an ocean, a global ocean as well. And this ocean is actually an excellent candidate for life. It's the properties of the ocean that make it such a good candidate for life, and I'll show you why in a sec. The colours on Europa, the yellow has been proven or shown to be just ordinary NaCl, table salt, which has come up from the ocean beneath. I'm pretty sure it's come up from the ocean beneath. And the radiation around the environment turns sodium chloride that yellow colour, so that's pretty well established. The other colours there, the darker colours, are due to other salts and minerals, probably again from the ocean, coming to the surface, and probably a little bit of stuff from Io as well, landing on the surface of Europa. I think that's a more natural colour picture of Europa. Sometimes you see the slightly enhanced colours to show more features, but that's closer probably to the actual colour. It's very bright with its icy white surface. So I mentioned Europa has this global saltwater ocean, but unlike Ganymede, this ocean is in contact with the sea floor, with the rock below, and that means that nutrients can get from the rocks into the minerals into the ocean, which would provide food, I guess, for microbes which might live there, and also would be a help in forming life in the first place. AHV stands for alkaline hydrothermal vents, and these have been found on Earth. Pretty certain they're on Saturn's moon Enceladus due to the makeup of the compounds and the geysers that come from Enceladus. Now, alkaline hydrothermal vents are vents that form as seawater goes under the sea floor, reacts with the rocks. It doesn't need any volcanic activity. Reacts with the rocks, chemical reaction. The water comes up heated to about 60, 70 degrees Celsius, starts forming these chimneys. And the chimneys have these little pores which are about the same size as living cells. And it's thought that that may be where life might have started on Earth, because they're just the perfect size. And the acidic ocean and the alkaline water coming up has got that balance between, like we have in our blood in our systems, acidic versus alkaline, slightly giving a thing called a proton gradient, which is getting a bit more into the astrobiology here. But it's thought that that might have been a good possibility for how life started on Earth. So if that is the case, then we may have a good candidate for life on Europa, and it's thought to be one of those places where we'll look for life first if we can get under that ice. Now, another piece of evidence for the ocean, apart from the good old induced magnetic fields, are these geysers. So these geysers have been seen intermittently. These are 2 years apart, Hubble images, little plumes that have reached about 200 kilometres above the surface. And just over here, this impression over here, an idea of how this might happen. We have our ocean, cracks in the ice, where squeezing might occasionally just force the water up into these geysers. Alternatively, it is possible that the geysers come from pockets of water within the ice and not from the ocean below. Again, something we're going to have to find out. But if that is coming from the ocean, when we get there again in 2030, we've got Europa Clipper heading there as well. If it can fly through the geysers, if there was any life such as microbes, it would almost certainly be able to pick that up. So we may know in 10 years' time whether there is life there, microbial at least. Probably not much. Well, something bigger might be in there, but we've got to start with the small ones first, so not jump ahead too much. So here you are on the surface, another artist's impression. This is the hottest part of the moon. It's minus 150 degrees, midday at the equator in summer. The poles are about minus 220 degrees Celsius, so you'd want to stay here if you were going to if you're going to do anything. But you'd stay there for 24 hours because the radiation would be deadly. There's radiation all through this area. The radiation actually comes from the particles, a lot of it from particles, again from Io, which had their electrons stripped off the atoms, so it's atomic nuclei and electrons all flying around it at high speed. It does have as I mentioned, they all have this tenuous atmosphere. Europa, predominantly oxygen molecules, with a few oxygen atoms, bit of H2O and carbon dioxide. Now the oxygen comes from the water, so the radiation again breaks down the H2O molecules, splits it up into oxygen and hydrogen. The hydrogen generally drifts off into space and a little bit of oxygen is left hanging around in the exosphere. That radiation is not going to affect anything too much under the ice because the ice is thick enough to be a great insulator from the radiation. So if something did form under the ice, it's probably pretty safe, but it wouldn't want to come to the surface at all. So I don't think we'd really want to go to the surface of any of those moons, to be honest. We'll send the robots there. Right, and so kind of left a really interesting one to last here, and this is Io. This is the most volcanic body in the solar system, with probably 400 volcanoes, 50 to 100 erupting at any one time. And here's that image we saw before. That's the rather amazing infrared image of Io, which was taken by Juno in 2018. So Io was in the shadow of Jupiter when that was taken. Each of those spots is either an active volcano or a hot spot on the surface or just under the surface. But there's another image was taken by Juno, which I actually think looks even better. This was taken in 2022. And this is infrared again, but obviously with the sun just shining a little bit on Io there as well. Kind of looks a bit unreal. Almost freaky looking. Now, it used to be thought the volcanoes on Io were powered by a global subsurface magma ocean, a bit like the other moons had a global saltwater ocean. But recent research has shown that each volcano should be powered by its own little magma chamber. And that started from the Juno mission. So that's a bit of updated information since I think I last did this talk when it wasn't certain what the situation was. Now, due to the tidal effects that we talked about before, Io stretches and squeezes by about 100 metres every 42.5 hours. So that's like giant land tides of 100 metres up and down, which is pretty huge, really. And it's the friction from this that's heating the interior and keeping this magma molten. Interesting fact is that Io is the most dense moon in the solar system, and our moon is the second most dense moon in the solar system. So it just beats us at that record. And I mentioned before that Io loses gas to space at the rate of a tonne per second. Some of this actually turns into sulfur dioxide snow and falls down, and that sulfur dioxide scatters light and gives that kind of a blue colour. It's a bit like the oxygen or the nitrogen in our atmosphere scatters blue light and gives us the blue sky. This one up the top was taken by New Horizons as it headed out to Pluto, but the one down the bottom was taken by Voyager 1 back in 1979, I think it was. This is 2 months ago, that was the largest volcano on Io. Things change so quickly. This is Loki Patera, and that erupts about once every 500 days. It was just on the 27th of December last year, only about a month or so ago, that a larger volcano was discovered on the south of Io. So whether that's just something new that's formed or just hadn't been seen before. So there's a lot happening. It's changing a lot, the surface of Io and the volcanoes. Now, New Horizons even took enough photos to get this 5-frame movie of this giant volcano erupting here. There's another one, I think, down the bottom, erupting there, and probably a few more. Now, these plumes are about 290 kilometres high, so that's the Tavashta volcano. Now, if you think of 290 kilometres, that's 3/4 of the way to the International Space Station from Earth. So if you were, imagine standing on the surface of Earth and seeing a volcano erupting and its plumes going 3/4 of the way to the International Space Station, some of it turning to snow, and then the snow, sulfur dioxide snow, falling 300 kilometres down onto the ground around you. Quite an amazing sight, I reckon, to see. So it's a pretty fascinating moon, Io. But lava lakes have been found to be very common on the surface, and this is an animation of Loki Patera. That's that one we saw erupting just a moment ago. There's a photo on the top right of Loki Patera. This is the lava lake here. It's about 200 kilometres long from one side to the other and about 20,000 square kilometres in size, with islands in the middle. And here's Lake Taupo compared to size. So it's a very big lava lake, which obviously erupts quite often. The new thing that was discovered just recently is about 5 times as big as that, and maybe a group of 3 or 4 volcanic lakes together. But that was so new I haven't actually had time to put it into the talk.
If I may, what's the composition of the lake?
So that's all lava. So it will
okay.
be magma. The surface will be slightly crusting over. Apparently at times waves do come out, break the surface, it sinks down, becomes liquid again, and then will cool off again.
And the chemical composition of the lava?
There'll be a lot of sulfur. The sulfur dioxide is kind of what gives the volcanoes their power and kind of builds up from the bottom. So once Io runs out of sulfur dioxide, it probably won't really have as much volcanism occurring. So there'd be a lot of sulfur in there. So I imagine it would be, well, yeah, disgusting. The atmosphere again is very, very thin. So yeah, I guess you could smell it for a second.
So very close to the surface, it could be quite hot, but very quickly, rapidly.
Yeah. It's obviously hot enough to kind of keep soft for quite a while. So there's always a lot of heat occurring, and there'll be a lot of heat from underneath, I guess, keeping it warm as well. Yeah, internal pressure as well. So, but there are quite a few lava lakes around on Io. So about to wrap up now. This is the Io plasma torus. Now, most people probably haven't heard of this. It's a ring, or more a donut shape or a torus shape, made of charged particles that are orbiting Jupiter with Io. And these particles are mainly from Io's volcanoes. Now, just as an aside, here's the magnetic axis of Jupiter compared to the rotational axis. So the magnetic axis is on a slight angle. So as Jupiter rotates, the magnetic field as it goes past Io is kind of changing. And it's also changing with those other moons as well, which is helping to induce those induced magnetic fields. Now, as Io orbits Jupiter, it's orbiting at 65,000 kilometres per hour, but this torus is going around at 265,000 kilometres per hour. And that's being pushed around by this magnetic field, because Jupiter takes about 9.9 hours to rotate, and so that magnetic field on the angle is going around at the same speed. So these are being pushed around by the magnetic field at 265,000 kilometres per hour, overtaking Io at 200,000 kilometres per hour. So now you're standing on the surface of Io with charged particles whipping past you at 200,000 kilometres per hour, ripping off a lot of the atmosphere of Io, adding more to the torus there and spreading it out through the system. So it's not a great place to be. And it's actually electrons that are hitting the particles in the atmosphere and stripping electrons off the particles and sending it out the atomic nuclei and the electrons to add to this torus. Now, the magnetic field, as I said, is not aligned with the rotational axis, and that is why this is all happening and why it's moving this torus around at such high speeds. And here's a photograph of the torus. It does emit light in wavelengths from infrared through visible and right through to ultraviolet, but the wavelengths in the visible are so weak that we can't see it with our eyes, and so we have to get these photos, or this photo was taken using wavelengths outside the visible wavelengths. So we actually see that torus. But there's even more to all this. All that plasma that's rushing past Io at that high speed is setting up a voltage across Io of 400,000 volts. And this is resulting in an electric current of 5 million amps. So it's getting better. So don't go to Io. And this current actually travels through Jupiter's magnetic field, and it's reaching Jupiter's poles, and this is called the Io flux tube. So remember that picture we had from the start. We can't see the flux tube, but we can see the effects, and here's that thing at the top. This is a movie made with the ultraviolet picture of the aurora on Jupiter. And when it stops, I've just drawn the flux tube to show you. So that's kind of where the flux tube's hitting Jupiter. Same will be happening on the South Pole as well. And that's called the Io spot. So here it is again. So that's the Io spot sitting up the top. Yeah, so as Io is going around, that Io flux tube is coming around. Jupiter's rotating that way, and Io is behind. Yeah, so that's why it looks like it's moving backwards.
So when they send, spacecraft, how do they shield them?
Well,
all that current.
Yeah, when Europa Clipper goes to Jupiter and studies Europa, it's actually going to have a very elliptical, eccentric orbit, and it's going to go to Europa, get some data, and it's going way, way out past the moons, out of the really high radiation areas, and send back data to Earth. Then come back in again, then go back out again, and it will eventually fry itself.
Just dipping its toes in and getting out quickly.
Yeah, pretty much, yeah. Juno will be Juno's the same. Yeah, and it'll be the same with Juice as well when it gets there, so they will have to go and keep out if they can. Yeah. The what, sorry? No, I hadn't heard of that. That's actually interesting.
Observable on the voyage in Galilean, the actual honest business fault from the surface of Io to the cloud tops of Jupiter every once in a while.
Oh, okay. That's actually something I hadn't seen, interestingly enough. Yeah, fascinating. Yeah, yeah. And another reason not to go there in your spaceship, I think. Yeah, it's not a fun place, is it, to go? But actually, there's even more. So we've got the Io spot, but you can see two more spots down there. There's the Ganymede spot and the Europa spot. So there's a bit more happening. Of course, not quite as dramatic as the Io spot, but obviously, with what you're saying, with what else is happening there, there's probably even more things happening there that we haven't found yet. So it's a fascinating environment, really. It'd be neat to go there, but it wouldn't be neat to go there. So. If you didn't want to come back, I suppose. So I'll finish up now. We've seen Jupiter has 95 confirmed moons. We've got the 4 irregular moons, the 4 Galilean moons, and those 87 irregular moons. The irregular moons, we saw are very small and seem to be the remains of shattered larger objects, and they've got really large eccentric orbits. The Galilean moons, we've got those 4 large moons, some with oceans, one with active volcanoes. They all have auroras, and we've got the natural magnetic field on Ganymede, of course lava lakes as well. And then not forgetting those 4 inner moons, the Amalthea group, those small oddly shaped regular moons. So I think the final word is really that next time you look at Jupiter through a telescope and see those 4 bright dots, you can think about all those other things now that you didn't know were there and that you can't see. And yeah, just be even more fascinated by what's out there. So thank you very much.
Thank you.
So if there's any questions, if there's anything left to ask.
Very, very interesting.
Thank you. Hello.
With the thing is the tidal forces, this sort of expansion and contraction, heating up the moons, is there tidal locking? Is that part of it?
Oh yeah, they are tidally locked.
All in one face.
They all have one face. In fact, what did I have? I thought I might have had something here. Yeah, so they've all got one face towards Jupiter, and I guess one of the interesting things is the closer to Jupiter, the more gravity, but the front face has a greater pull towards Jupiter, simply because it's closer to Jupiter, and so it gets stretched. As it gets further out, the total gravity is less, but also the difference is less too. So that's why you have it squeezing back and stretched. And yes, they are all tidally locked as well, just like our moon is towards.
You get more force, the greater the ellipse.
Yeah, pretty much. The greater the ellipse, you get further away, so you can have more stretching and squishing. Stretching, squishing, yeah.
Is there any relativity with the orbital velocity of the moons, Galilean moons?
Like special.
If you've got a narrow orbit, it appears to be moving faster, but are they roughly?
I don't think the speed would be enough to make too much of a difference. Well, not enough to make any physical difference, but if you're going to put, I guess, GPS satellites on it and that kind of thing, you would have that kind of relativity. Yeah, so I guess if you're measuring precise information, you would have to take that into account, just like with our GPS systems, yeah.
You started off the presentation around what is a moon, and we recently had a second moon come into Earth.
Oh yes, that was a mini moon, yeah.
And the fact that it came in and went, was that meant as a moon, or is it going to come back at some stage?
Yeah, interesting that they called it a moon. They called it a mini moon mainly because for a short time it's within the gravitational field of Earth enough that the gravitational potential energy is greater than the kinetic energy, so it's essentially called captured. But it only lasted for about a quarter of an orbit, so that particular one was only really a mini moon for a short time. We did have one a few years ago which lasted quite a few months, or actually might have been years, and kind of a erratic orbit all over the place until it finally escaped, because its velocity with respect to the sun and the moon, sun and the Earth, was such that it was just eventually going to have to escape anyway, but it was just captured for that short time. So they call those mini moons, which is kind of pushing the word moon, I guess, in that particular case, but it's kind of, I guess it is a natural satellite for a little bit. Yeah. And we have the quasi-moons as well, which are the ones that don't orbit us at all, but orbit with the same year, and so they look like they orbit us because they go in and out of our orbit, and we kind of follow them around, and so they look like they have this orbit around us, so they're kind of called quasi-moons.
Do you happen to know the space probe Juno? Where is that relative to all these small moons and stuff?
Yeah, so the small moons are a long way out, so Juno is kind of closer in to the larger moon, so the system is pretty big, and I think getting photos of a lot of those smaller moons seems to be quite tricky, because I don't know how easy it would be. I guess if you sent something specifically for that, we could go and have a look at quite a few of them. Interestingly enough, Juno was meant to be retired, I think, 2021, and they've left it going until this year, 2025, because it's doing so well, getting so much information. Yeah.
Quite amazing how they avoid contact with objects because there's a lot going on.
Yeah.
How do they do that?
I guess the thing is there is a lot of space, and so the odds are that, well, I suppose the longer they stay there, the more chance there is, and that's probably why those moons collide, but over billions of years. So what we see now could have taken a long time before they actually did manage to crash head on, or whatever it might have been.
Voyager's still intact out there somewhere, right?
Voyager is, yeah. So that's pretty safe out there. That's pretty clear going. Even going through the asteroid belt, you'd be pretty lucky to hit or see anything. Yeah. So I think someone I missed before over there. Yeah. Oh, Joel. Hi.
Yeah. There's a good theory how our moon formed. Good theories. But what about, say, the Galilean moons?
So the Galilean moons would have formed with Jupiter from pretty much a disk of gas and dust. So they would have coalesced and just sort of formed at the same time. So they're thought to be about the same age, roughly, as the solar system. So
in locked into Jupiter, there'll be similar materials.
it's interesting because there is a lot of ice there that's sort of formed around those ones. I guess Jupiter grabbed most of the gas and kind of just left. And I suppose if there was gas around those ones, it would have been kind of drawn into Jupiter. Interestingly enough, you talk about that Saturn's moon Titan is a very thick atmosphere, but that I think is being replenished from underneath. So maybe they might have had. Yeah. So it's kind of being peeled off a bit, but it's also replenishing. So
what's surprising is the amount of water. In other forms, the amount of water that's out
there is, yeah. So water's, when you think about it, hydrogen's the most popular. Well, not most popular, the most common element in the solar system. Helium next, and I think oxygen might be the third most common element in the universe, if I'm right. And so water tends to be a very common element, which is great. So our search for life will be hopefully fruitful at some stage, yeah.
So some of the models had Jupiter much closer to the sun earlier on, and that migrated out. So I wonder when the moon formation occurred, like did it occur as Jupiter migrated out, or did it when Jupiter was closer in?
That's a really good question. I guess it is possible that there were other moons that formed, larger moons. Some might have got pulled in or lost with the migration. So things could have changed quite a bit. So they might not be quite the 4.5 billion years old. Callisto's surface seems to be about 4 billion years, but 500 million years is enough time, I guess, for more to form and lose a few. Yeah.
Collisions, like with the moons, are collisions very common between regular, what's the term? The regular.
Oh, the regular moons, or yeah.
Do they collide with each other, or is it more just other?
It's more stuff coming in. So when that gets captured, it comes in and might crash into something. And sometimes that actually might help to catch the moon because they crash, lose some energy. The pieces end up orbiting. Some might fall in. Some get ejected from the system. The regular moons, because there are probably just the 8 regular moons, they're kind of probably pretty safe, and all the rest will be irregular. I guess it's possible you can capture something that come in and smash into one of the regular ones as well. So anything's possible. Now, do I see someone over there? No other questions?
That was a very interesting visual presentation.
Thank you very much.
We did what we did.